I'm going to give a survey talk in various topics, but I will assure you that I will follow a logical path, essentially focusing on ideas rather than details, and I can give you some details depending on the time I may skip. So I'll first start with the motivation, which is pseudo-Hermitian quantum mechanics. I'll introduce these words: transfer matrix, spectral singularity, unidirectional invisibility. Then I will discuss properties of transfer matrix which was not known. For example, I'll show that it is actually an S matrix for some non-unitary system. I will derive dynamical equations for transfer matrix and use it for various purposes. For example, to give a general model for unidirectional invisibility. I'll discuss perturbative invisibility and perturbative scattering theory, inverse scattering theory, which is very simple in this language. Then I will explain how adiabatic approximation and semi-classical scattering are related, and how you can identify something you have seen since undergraduate quantum mechanics in the scattering wave WKB approximation, geometric phases, which is there already. And then I will talk about this local inverse scattering. Depending on time, I may skip some of the details. So, So, for me, the subject began in 1998 by a paper by Bender and Becher, although I learned about it 3 years afterwards. They noticed that if you take Ix3 potential, although this is a non-Hermitian Hamiltonian, it does have a positive discrete real spectrum. And they gave a reasoning. They said, well, this is because this operator commutes with PT. P is parity, reflection about 0, and time reversal is just complex conjugation, T. And obviously, if you change x to minus x and complex conjugate, this is invariant. P is also invariant, so this is PT symmetric. However, if you, for example, take this operator Ix, that's also PT symmetric, and it obviously has an imaginary spectrum. It's continuous imaginary spectrum. Or there are many examples. Well, what is the spectrum of X? It's real line, so it's Ix, it's I times R. It's imaginary axis, the spectrum.
You can argue about X cubed in the same way. About X cubed, you can argue in the same way. X cubed.
Yes.
But it has real spectrum.
Yeah, but so what I'm saying is that this PT symmetry is not sufficient. This is a counterexample. And also, it is not also necessary, because take these complex potentials, they do have real spectrum. They are not PT symmetric. Z is an arbitrary complex number. So I could not see why they are insisting. But the idea that maybe you can use this kind of operators in quantum mechanics as Hamiltonians or some sort of observables. And the question becomes, can you do that? Well, if you want to accept the projection axiom of quantum mechanics, I do not know any theory of quantum physics that can reject it or even perturb it. It's very solid and fixed axiom. Then observables, if you agree that they are linear operators, they should be diagonalizable and they should have real spectrum. The word diagonalizable I have to define. So suppose you have an operator which has a discrete spectrum. I will say it is diagonalizable if you can construct pairs of eigenvectors of the Hamiltonian H, the operator H and its adjoint, satisfying, so psi's are eigenvectors of H, phi's are those of H dagger, and they will satisfy these by orthonormality and completeness relation. Then I will say, if such a system exists, what I call an eigensystem, then the Hamiltonian I will call diagonalizable. So the basic question becomes, what is the sufficient and necessary condition for a diagonalizable operator to have a real spectrum? And the answer is this. This is necessary and sufficient condition. The H dagger should be related to H by a similarity transformation. generated by a positive definite metric operator. There are technical conditions on 8 plus, should be bounded, inversely bounded. They will not, they can be also avoided by other means. So this is it. Well, what does this eta plus does, actually, the basic outcome, interesting outcome, is that you can use this eta plus to modify the inner product of your Hilbert space. After which, the initial operator, which was not Hermitian, becomes Hermitian. So you kind of hermitize your non-Hermitian operator, and this should hold, otherwise you can't. Well, this eta plus is not unique, but there is a spectral representation for it. Phi's, remember, are eigenvectors of H dagger, and any metric operator will have this form. The only difficulty, or the point, is that these eigenvectors are not unique, so you get different types of eigenvectors giving you different metric operators. And these results started to be published in a series of 3 papers I published in 2002, and then I worked it through several years. So what I call pseudo-Hermitian representation of quantum mechanics is that you construct this new Hilbert space out of this modified inner product, and then your operator becomes a self-adjoint Hermitian operator acting on that. So if you take a quantum system, define it by this Hilbert space, you see Hilbert space defines the kinematics because observables are by definition self-adjoint operators, and H, Hamiltonian, defines the dynamics. So this pair defines you in a unitary quantum system. Furthermore, if you take the square root of eta plus is a positive definite operator, it has a unique square root, and then view it as an operator mapping the new modified Hilbert space back to the old one. These have, as vector spaces, have the same structure, but the inner products are different. When you look at it that way, this turns out to be a unitary operator, and you can define a Hermitian operator in the initial Hilbert space, which is unitary equivalent to your non-Hermitian Hamiltonian, and then you have 2 different pictures of the same quantum system. Either you modify the Hilbert space and keep using your initial Hamiltonian, or you keep the initial Hilbert space and modify your Hamiltonian. They are unitary equivalent, and they have the same physical output. So you see, you don't get a lot by doing this, except that this H, as I will show you, will look horrible when you use this picture. This is what I call Hermitian picture. This is pseudo-Hermitian picture. And in both pictures, what is important is eta plus.
Will eta plus look horrible in another picture?
Eta plus is fixed, and it has the same form in both pictures because it commutes with rho. Rho is the square root of eta plus, so that is the same. And this is a big review paper that explains everything. So this is one of the earliest examples of this PT symmetric. It's Ix cubed with the harmonic terms, harmonic oscillator modified with Ix cubed. You can calculate metric operators for this perturbatively, and here is one such I've used one such inner product to get the equivalent Hermitian Hamiltonian, and as you will see, it has all powers of P, and as you go higher and higher, you have higher and higher powers of P. So it is not a differential operator, it's a non-local pseudo-differential operator. And you don't want to work with this kind of thing if you, for example, want to calculate the spectrum.
Is it even in X?
Yes. And in P. That's right.
What's the explanation for this?
I think because this is an odd function, that is the reason.
And what are your curly brackets?
Oh, anti-commutator. No, anti-commutator. So these are self-adjoint. Yeah, it's an operator. It's quantum mechanics. I will not discuss classical mechanics at all. Everything is quantum. Another, actually exactly solvable model, which was considered much later in 2006 by me, is a delta function with a complex coupling, which can be obviously solved exactly. And again, you can try to compute metric operators one such metric operator, which I have computed again perturbatively in imaginary part of the coupling constant, has this form. Again, this piece is just the real part of the coupling constant, and the first correction comes as again second order in imaginary part. And this is an operator which is very, very strange. It's a linear operator which takes every wave function to an exponentially decaying one plus the delta function. So you would say, so how does it depend on psi? It depends in terms of these constants. And dependence is just the zero of psi, and then this part is non-local. It involves the integral. And in this formula, as you see, there is this L, some length scale, which has the real part of z in the denominator. And that's already a problem. And so you might ask, well, what if the coupling constant is imaginary? When I did this, I spent days to compute things with imaginary thing, and every time I was trying, because you see this is a scattering problem, the levels are doubly degenerate, so you have a lot of freedom in the construction of eta, but whatever I did, it blew up. So I realized that you can't have a metric operator when it's imaginary. And then I realized that this might be related to something mathematicians call spectral singularity. At that time, I barely knew what it meant. I didn't really knew what it means really. I got a mathematician to help me learn about it. So that turned out to be actually more interesting. So let's review scattering theory. So suppose you have scattering potential, which means it can be complex valued. It can even depend on energy, very general, but I want it to vanish fast enough at infinities. For example, if it's finite range, that will do. Well, asymptotically, the potential vanishes, so the solutions of the equation are just plane waves, but the coefficients at plus or minus infinity don't need to be the same. And there is a matrix which connects the coefficients at minus infinity to those at plus infinity, which is called the transfer matrix. You can show it has the unit determinant, and it turns out that spectral singularities are the zeros of this entry of the transfer matrix which lie on the real axis. So this is the simplest, most straightforward definition of a spectral singularity. Obviously, it took me like 2 years to find it, because mathematicians don't discuss it like this. So for the delta function potential, you have an exact, very simple formula for the transfer matrix. So you want to look at if you have zeros of this, and obviously a real zero exists if z is imaginary. And this is spectral singularity, and that was the reason my procedure didn't work. Oops. So then I try to understand what this spectral singularity means in physics. So here is the definitions of left incident and right incident scattering waves. In complex potentials, they are different because left and right reflection coefficients can be different. You can easily relate these are the R's are for reflection, T is for transmission amplitudes, complex amplitudes, and they are related to the entries of M by these formulas. You can show that the transmission from left and right are the same, and that comes as a very nice application of Abel's theorem in differential equations that we teach in sophomore level. And you will see immediately what will happen if M22 vanishes.
All potential, all complex potential.
All complex potentials. In literature, even mathematics literature, some places they say it holds for real, but it's also true for complex. It's a Wronskian identity, essentially. So what happens if M22 vanishes? Well, you see, reflection and transmission amplitudes blew up. M12 and M21 cannot be 0 because M is unit determinant. So if M22 is 0, then off-diagonal entries cannot be 0. So all of them blew up. So what does that mean? It means that if you send any signal, it is infinitely amplified, and it comes out of both ends of your scatterer. Well, so you have outgoing boundary conditions. That's also a definition of a resonance. But you see, this resonance has a real energy, which means its width is 0. So this is a scattering state which behaves exactly like a resonance. So I will call it a zero width resonance. This I did in 2009, but it again took me a few years to find a very nice manifestation in physics. So let's do electrodynamics, actually waves, electromagnetic waves. Suppose you have an infinite planar slab in the xy plane. It has some thickness L, and you're sending electromagnetic waves from the left. This is incident, transmitted, reflected, okay? And you fill the slab by some active optical material which can be modeled using a complex refractive index. I will take it to be homogeneous, so eta and kappa are constants, real imaginary part of n, and then you see what happens inside. Inside you have this solution. It's polarized along the x direction, and this is a very simple solution of that because this is a constant, and you substitute this n in here. You see the imaginary part will get you an exponentially decaying or growing piece. This is oscillation. So when kappa is negative, what happens is that the wave grows exponentially inside your medium. And such media are called the gain media. If kappa is positive, it's a lossy media. It absorbs, and you get. And if you look at the intensity of the wave in a gain medium, it grows exponentially with this as exponent times z. And this is called the gain coefficient. This is the definition of gain coefficient. Now, go back to the whole system, not inside. Well, you can get a solution of the wave equation in this form, okay, where psi satisfies the ordinary time-independent Schrödinger equation. What is the potential? Oops. The potential takes this form. It's a barrier potential whose height is related to n, which is complex. So this is a complex barrier potential. Obviously, it's a complex scattering potential. It vanishes at infinities. So this is a very nice, a simple example in which I could look at what the spectral singularities are. Oops. I think I should stay closer. So you calculate this, which is exactly, can be done exactly. It's constant barrier. And this equation, after a few lines of calculation, can be written this way. Now, I wrote this and sent it to a physics, Journal of Physics B, or Physical Review A, I don't know. And one of the referees said, well, the right-hand side has a name in optics. It's called the reflectivity. I never took a course in optics, and I had to learn all this later. If you take this equation, take the absolute value of both sides, only imaginary part of n comes, and you can relate it to this g, and you have this equation. You take the logarithm, you get a formula for this gain coefficient. It turns out that this exists in almost every optics book, and it has a name. It's called laser threshold condition. Spectral singularity is nothing but lasing. Spectral singularity was discovered by Naimark, forgot, 1950s, early 1950s, before lasers, a few years before lasers. I mean, if mathematicians had this, they could discover lasers before physicists. So in optics, a spectral singularity is lasing at the threshold gain. Once I gave a talk on this in a conference, and the chairman was eminent optics people, and he said, well, this is all known. You have discovered the wheel, and then you said, no, you have discovered lasers, which is very, very important. But people knew about it, but not the mathematics. They didn't know. So what happens if you do the time reversal of this effect? So in a laser, radiation comes out. You don't send anything. Infinitesimal noise gets amplified, and you get a finite amplification of waves coming out. And the time reversal would be you send the same radiation in, and nothing will happen. It should be absorbed. This is also called an anti-laser. It was discovered in 2010, 1 year after my paper. And it has certain applications. This is also called coherent perfect absorber. There are dozens of papers on this. Okay. So what about unidirectional invisibility? So that was spectrosingularities. So unidirectional reflectionless means one of the reflection coefficients are 0, or amplitudes are 0, and the other is not.
Just to understand,
yes.
You mentioned the delta function, imaginary height delta function potential. You said that always has a spectral singularity.
That's right.
So it always acts as a laser?
Yes, yes. Obviously, it would be difficult to, so you have to have a very, very thin slab with very, very high gain. So.
But it's spectral singularity at the particular?
Yes, at one frequency. You always have a finite number of frequencies, but that can be increased. Okay, so this is reflectionlessness from one direction. If in addition it is reflectionless from one direction and the transmission amplitude is identically 1, then it's called unidirectionally invisible. So if this happens, what is, you send the wave, suppose it is from the left, wave goes in, doesn't change at all, amplitude or phase don't change, and there's no reflection. So there is no way you can see the scatterer. Whereas from the other side, there is reflection, you can see it. So this is genuine invisibility. Again, this was published in PRL in 2011. There were a few papers beforehand, but essentially this paper made it famous. I think it has like 150 citations in 3 years. So now, if the potential is real, you can show that the left and right reflection amplitudes must have the same modulus, absolute value. They can have different phases, and you have unitarity relation. So this excludes unidirectional reflectionness and invisibility. This excludes spectral singularities because you see T and R cannot be infinite. They are bounded, less than 1. So all these effects need complex potentials. Now, this transfer matrix which I introduced has this very nice property which makes it so important and useful in various areas of physics, mathematics, and even engineering, in discussing exploring multi-layer systems, optical crystals, and things like that, is its composition property. Suppose I have two potentials whose support does not intersect except at one point. That is, whenever one of them is non-zero, the other one should vanish. And this is their sum. If M1, M2, M are the transfer matrices for V1, V2, and V, you can show that M is related to M1 and M2 by just matrix multiplication. Remember, this is unit determinant matrix, so this is in the group SL2C. So this is just a group multiplication in SL2C. Now, a couple of years ago, it occurred to me that this is the same composition rule for evolution operator in quantum mechanics. If U is the time evolution operator, to evolve it from T0 to T2, you can evolve it to T1, and then from T1 to T2, right? So I said, can I write these M's as evolution operator for some quantum system? The idea there are two ideas that made this possible. The first one is to go from the Schrödinger equation to a time-dependent two level Schrödinger equation. That is essentially, you write the second order differential equations as two first order system of equations. The tau will be not time, it will be some evolution parameter, which is nothing but k times x. K is the wave number.
Well, may I ask you a question?
Sure.
Earlier, you started with your metric operator, and you explained to us that
right.
Then you said when there's a spectral singularity, it doesn't work.
That's right.
Can you elaborate on this? Why? What doesn't work?
Oh, the metric operator doesn't exist. Yeah.
So basically,
You can't construct.
this imaginary
Yes.
delta function does not exist.
That's right. That's right. Okay, so what I did here is to introduce evolution parameter. I wrote my psi in terms of new tau variable. I call it phi. Dot means derivative with respect to tau. W is just the potential in the new parameter rescaled by 2k squared. K is the wave number, which is like a label which doesn't enter into calculations. It sits there. It's 2 pi over the wavelength. Yes?
Question. What is the general condition for this metric operator not exist? Just it's enough to have one spectral singularity?
No, there may be like Jordan block things. That also is a obstruction. So they are called exceptional points. So there are two types of generic obstructions: the presence of spectral singularities and exceptional points. Exceptional points come in the discrete spectrum, spectral singularities come in the continuous spectrum. But I didn't want to go through that because this is already
Another question. What's your philosophy? Some Hamiltonians can be unitarities,
right.
Intuition.
Right.
Some cannot.
That's right.
But now for applications, you don't want them to be Hamiltonian.
That's right, because you get
Active media and so on.
right. You get nice applications. Well, the other one has also applications, but this is a kind of
You take a Hamiltonian from here, which has applications in optics, it's
Right.
non-Hamiltonian, and
Right.
then you make it Hamiltonian by choosing a metric operator.
but I cannot. You see,
Some of such things you will be able to. There is no spectral singularity.
then you see, like in finite dimensions, they are unitary equivalent. So you don't expect to get something new. See, there is a paper in 1942 by Pauli in which this is written. He says don't consider these non-Hermitian ones because they are equivalent. Well, he is right, and also he is not. I mean, they are applications.
But you see, here you're talking about non-unitary
Right.
evolution operators.
Right.
In the other picture, you will get a unitary evolution operator. So something is not equivalent.
Oh, I mean, from one you can define you hermitize. You can hermitize, and afterwards you have unitarity. Right. Here I don't do that. For respective singularities, it is not possible to do it. For this one, well, generically for complex potentials, it's not possible. Sometimes it is. Okay, so let me go back. I'm trying to write this in this form. So I introduced tau. Phi is just psi new variable. W is just potential in the new variable, rescaled. And then I used a definition for a two-level state using phi and phi dot. See, all this began because I had used this many years ago when I was doing quantum cosmology. And the connection was that. So when you do this, then there is a Hamiltonian of this form, under which this is equivalent to that. The Hamiltonian is a 2 by 2 Hamiltonian, obviously, and it is obviously non-Hermitian. See, this W is a complex potential. Even for real potentials, it is not Hermitian. It's generically non-Hermitian. It's a two-level system, but if the potential is real, it becomes pseudo-Hermitian because it satisfies this equation. Eigenvalues of this is just this n, which in optics becomes the refractive index. Very convenient, plus minus of that. And what happens if v of x makes this 0? The eigenvalues collapse. The Hamiltonian becomes non-diagonalizable, and that's precisely the turning points in the classical system. So turning points in classical system correspond to exceptional points of the quantum system where you develop a Jordan block type thing. So now, the Hamiltonian can be written this way. This n is this matrix. U is its evolution operator, this definition of the evolution operator, and then you don't have the potential. When you have a free particle, the Hamiltonian is just minus sigma 3. Sigma 3 is the third Pauli matrix. This, and then I could, by few lines of calculation, express the transfer matrix in terms of the evolution operator of this Hamiltonian and evolution operators and its inverse of the free particle. And then I realized that this is nothing but precisely the definition of S matrix. So transfer matrix of scattering theory is actually a non-unitary S matrix for this two-level Hamiltonian system. Then I went to the interaction picture, the way you do always in field theory, right? Interaction picture Hamiltonian has this very nice structure. The potential factors out. This piece is universal. It is explicitly time dependent, this effective time dependent. And then I looked at this Hamiltonian. It's bizarre. It is not diagonalizable. Its spectrum is 0. The worst possibilities. It is pseudo-normal. Pseudo-normal means that the Hamiltonian commutes with its adjoint, but this is pseudo-adjoint defined by this sigma 3. And if it is real, it is again Pseudohermitian. If you take the evolution operator in the interaction picture, you can identify it with M. So transfer matrix is actually the asymptotic evolution operator in the interaction picture. That's also definition of the S matrix, right? So I know that the evolution operator satisfies the Schrödinger equation, right? So can I find a differential equation for M? Remember, M is the asymptotic value of the evolution operator from minus to plus infinity. How can I introduce a parameter dependent M and write differential equation for M? That required a second idea, and that is the following. Suppose you have this potential. I only picture the real ones, but everything works for complex. Suppose I cut it, truncate it at an arbitrary point in space. So if you take this and call it VA, obviously it depends on A, where I truncate. And what happens if I look at the transfer matrix for this? You see, transfer matrix for this is the evolution operator interaction picture from minus to plus infinity. But from A to plus infinity, nothing happens. Potential is 0. Interaction picture Hamiltonian is proportional to potential. So Hamiltonian vanishes. So after this point, the evolution operator is 1. So evolution operator for this truncated potential is the evolution operator of that from minus infinity to A. Okay? So I have this, and now I can use the Schrödinger equation to get a differential equation for the transfer matrix. Obviously, if I take alpha to minus infinity, it's 1. There is no potential. The potential is 0. If I take it to plus infinity, I recover the initial potential. Now, remember, transfer matrix has unit determinant. It is invertible. Multiply this equation by the inverse, you calculate, you get the interaction picture Hamiltonian again. Now, this occurred to me to be completely non-trivial. What does it say? It says, take any complex scattering potential, compute these M alphas, invert, take the derivative, multiply, you get the potential out, and this piece is universal. The simplest example is barrier potential. You calculate this M alphas, and they look horrible. You see, they have cosines. This n is just the refractive index. Sines exponentials. This is M11, M12, M21, and M22 are related. Yes, yes. So I define this MA. which is VA of x, which is V cotted, so this is like V of x theta of A minus x. That's the definition. And the transfer matrix for this I call M alpha. Alpha is just K times A. This is just a dimensionless parameter. So take these formulas, construct M, differentiate, invert, multiply, and this is not even continuous. You precisely get that. So that was my check. Actually, I first did it by hand and I made a mistake, so I said this is wrong, and then I did it with Mathematica. It worked. Okay, so this is the differential equation. It's initial value problem for transfer matrix. Now remember, transfer matrix is related to the reflection transmission amplitudes. This satisfies the differential equation. Well, these should satisfy differential equations. Obviously, these are very complicated nonlinear differential equations for R's and T. Fortunately, I could decouple them after, I don't know, 20, 25 pages of calculation. It requires a new set of variables. So suppose I have a finite range potential, so the potential vanishes outside some interval. You can get the other potential by taking the limit of the endpoints to go to minus plus infinity, and you introduce a new variable, z. So this alpha runs in real line, z runs a unit circle in complex plane. So it starts from, so suppose this is tau minus k, so it goes and in there, so this is tau plus, oh sorry, so x plus x minus, the potential finite range from x minus x plus, here it's non-zero, outside is 0, okay?
Just to understand the motivation.
Yes. No, not yet. I'm just trying to get equations for R's and T and try to decouple them. Once you go around this variable which runs over the unit circle, I should not, I mean this is wrong, this is what I call z minus and z plus. The definitions is over there. Okay? In terms of these new variables, the differential equation can be decoupled and solved, and everything can be written in terms of a single function s. This s function, this z, remember, runs around the unit circle. So this s satisfies a differential equation. It's a linear second order differential equation. This v wedge is essentially the potential in the new z variable written, and this is initial value problem. Z minus is the initial point, corresponds to the point to the left, and z plus is the end point. So you have boundary conditions at z minus, so it's initial value problem, second order differential equation, solved on the unit circle. So what is it good for? Well, you see, the relation between s and t and this r is very simple. This can be used for inverse scattering. Why? Because, well, suppose you want to have a t of this form, well, you cook up an s which would give you the same transmission, then you have the s, you put here, get the potential out. Just taking derivatives. Example, suppose I have a spectral singularity at some wave number or wavelength. Well, I just need this to blow up. That means s prime is 0. I need just an s with a pole. I mean, with a 0, not a pole. S prime with a 0. This work is a polynomial. It's well defined under these conditions. It corresponds to a refractive index profile of this form. It's a finite range. And remember, these are complex numbers, so it has loss and gain regions. It's periodic, locally periodic, and this is guaranteed to give you a spectral singularity at k0, and k0 is your choice. You can build a laser which works at any frequency you want. This is experimentally not very easily done because this can be large. But you can cook up other examples. Oops, yeah. So now I want to get a right invisible potential using that. So right reflection should be 0, transmission should be 1, and I make sure that after I come here, this happens. So for z, the end value of z, this happens. This is a simple choice. It involves this alpha parameter, which is a controlled parameter for me. It's not the alpha that I used before. It's my choice to choose alpha. And well, it gives me this refractive index profile in which, and I also make the length of my support. The potential is from 0 to ln, and ln is pi n over kappa 0. N is an integer, so I can make it as long as I wish, or as small as I wish. And this gives you a particular loss gain profile. Alpha is here, remember, and n is there. And this is the corresponding potential. Why have I introduced this n and alpha? Because it allows me to tune and get any left reflection that I wish. You see? It is invisible from the right, but it has some reflection amplitude from the left. By working through this alpha, I mean choosing n and alpha properly, I can increase the reflection from the other side, or decrease it. And also, because I have taken ln to be pi n over k0, I'm going around the circle. And this n is the winding number, how many times I go. This is good because the equation which had an integral now becomes contour integral. I can do it very easily and exactly. So with these choices, you get this exact value for the reflection from the left. From the right is 0, t is 1, and this is it. N and alpha are my choice. N can be large, alpha can be small, so I can get anything, except the phase. Phase can be also obtained by moving, by translations of your potential. Translation gives you phase factors in the reflection that you can show, and that is how it works. You give me any complex number, and you ask me, build a potential which is right invisible and has this r as its left reflection amplitude. Here how it goes. You take the absolute value, you solve this equation, you get alpha and n properly, which satisfies this. This can always be done because alpha can be as small as you wish and n can be large. And then you use the phase to shift the potential that I gave you, the position of the potential. This m is an integer, so the support of the potential I can place anywhere in the real line. By changing different m's, I'm moving the potential to the left and the right. And this gives you the right invisible potential with given left reflection, and using the properties of the left and right reflection amplitudes under time reversal. And you can show that if you take this potential, you get the corresponding left invisible ones. So this calculation essentially gives you a general model for unidirectional invisibility. I will be using this later. How much time do I have?
10 minutes.
10 minutes? Well, I have to hurry. Okay, so let me do this fast. Okay, so you can do also perturbation theory very easily in this interaction picture because potential is out. So you can expand in Dyson series and do perturbative scattering order by order very easily, to any order you wish. The first order just gets you the Fourier transform of the potential. The second one gets you Fourier transforms of mixed potentials like this. You can do perturbative unidirectional invisibility. The first potential which was studied, and there are, I think, over a dozen papers written, is this potential with this exponential factor, which is perturbatively invisible. But I have full formulas for perturbative first order perturbative scattering, so I have a complete characterization of this phenomena of invisibility perturbatively. I use it, for example, to construct a very, very interesting device. It is invisible from the left for all frequencies, which are, wave numbers which are multiples of this k, integer multiples, and it is right invisible for half integer multiples. Perturbative inverse scattering. You see, the first order correction to the transfer matrix involves the Fourier transform of the potential. So if you give me firstborn approximation scattering data, by taking inverse Fourier transform, I can get the potential. So it's amazing. The firstborn approximation determines the potential uniquely. This was known in the literature on inverse scattering, but here is just a one-line derivation. Okay. Now, remember I had this potential constructed, the Hamiltonian constructed, two-level system. This is explicitly time-dependent. If you want to solve the Schrödinger equation, time-dependent Schrödinger equation for a time-dependent Hamiltonian, you can't do exactly. The most favorable and popular approximation is the adiabatic approximation. So I said, so what happens if I do adiabatic approximation? So what is adiabatic approximation? Adiabatic approximation says that if you take the eigenvectors of the Hamiltonian and you evolve them, they stay eigenvectors, but they differ by phase factors. I have a non-Hermitian Hamiltonian, so these are not really phase factors, they are complex numbers. Okay, this is the content of adiabatic approximation. Remember, the eigenvalues are just plus minus n. N is the refractive index defined by the potential, and these are the eigenvectors you can easily calculate. So the phase has two pieces. One of them is called the dynamical phase. The other part is called the geometric phase. This is nothing but Berry's phase, but the non-Hermitian version of it, which was known. So to calculate those phases, you need to calculate the eigenvectors of H dagger, which form this eigensystem for you. Phi's are the eigenvectors of H dagger. They satisfy, you make sure they satisfy these relations. And then you can calculate the dynamical phase angle. Really, it's not an angle, it's a complex number, and so the geometric one. And this is standard generalization of Berry's connection. This all written in this Garrison and Wright paper of 1988. And obviously this holds under a condition that this quantity, and there's a derivative here, should be small. Okay. Oops. So let's write this condition in more explicitly in terms of n it takes like this. In terms of v it takes this form. And this should remind you of what you have seen before. Let's go further. You calculate this delta and gamma. Turns out that this gamma plus minus is the same thing. And delta gives you this quantity. Remember, this is the eigenvectors. You put them together. You construct this object, and this was related to phi using this relation. Phi related to initial solution of the time-independent Schrödinger equation that we started with. You put everything back together, you find the formula for psi. That formula is nothing but the WKB wave function. There, the pre-exponential factor comes from the geometric phase. So the amplitude of the WKB wave functions are geometric phases. This can be taught in undergraduate quantum mechanics even. So in this picture, WKB becomes adiabatic approximation. They are the same, and I have used it to develop semi-classical expressions for transfer matrix and even compute higher order semi-classical approximations in scattering theory, because there are higher order adiabatic approximations. Okay, the final thing is local inverse scattering. So this is the problem that defines the subject. Suppose you are given a wave number, arbitrary, a complex numbers r's and r zeros and t0. T0 should be non-zero. And the question is, can you find the potential which has these values for its reflection amplitudes and T0 for its transmission? at given wave number k0. And a simple and interesting answer or solution is the following. You can explicitly construct such a potential which consists of at most 4 of these unidirectionally invisible this should be unidirectional, not this is unidirectionally invisible, sorry. Oh, no, this is correct. So it's at most 4 these so there will be V1, V2, V3, V4. All of them are unidirectionally invisible. If the potential you want to build is bidirectionally reflectionless, so the transfer matrix is diagonal, then you will need 4 of them. If not, you will need only 3. This seems odd, but that's true. Well, I don't have enough time to show you how it works. The proof is just matrix 2 by 2 matrix multiplication. You just work through the decomposition of the thing. So I skip the details of this. So I will just tell you where you can use it. For example, you can use it to construct almost every type of optical device which works at given wavelength. For example, I used it to construct a doubler. It is reflectionless from both ends. You send the wave from any which side, it doubles the intensity and also shifts the phase by pi/2. I mean, this is just one choice. You can make this shift any angle. You can raise the intensity or absorption. You can do that. And this can be done with 4 potentials. And these 4 potentials are, remember, unidirectionally invisible, and I have a concrete model for them. So this is the same model I described. I don't go through. It had these alphas and n's and d's which I could fix. So this works in wavelength 1 micron, which is quite useful in many applications. I have taken n to be 300, so the length of my slab is 150 microns. And with these choices, which can be experimentally achieved, this corresponds to not very high gain or high loss material because I made this alpha very small. And you have, this is a numerical plot of the reflection coefficients in absolute value and t minus root 2i. Root 2i because the intensity goes like t, absolute value t squared, so it's twice, and the phase is pi/2, that's I. And you see at k equal to k0, all of them vanish, so t is root 2i and r's vanish. You can also construct Spectrosingularities. Take 2 potentials. One of them is to the left of the other one. One of them is left invisible, the other one is right invisible. By the composition property, this is the transfer matrix. Remember, spectrosingularity is when M22 is 0, so you can take this equal to 0. If you have this condition, it will have a spectrosingularity. And again, you see these are unidirectionally invisible ones, which I have a complete control. I have a model for them. So again, I have made choices on these parameters of the system. Again, the slab is 150 micron long, and this is the profile of the gain loss that can be. These are really not very difficult to achieve experimentally because they did the experiment with e to the I k0x, and these are, and alpha is small, so this is just the sum of 2 of those exponential terms. And here is the reflection and transmission amplitudes. They blow up this logarithmic, and precisely, this is again numerical thing. Okay, so let me summarize. Well, I began with discussing Pseudohermitian Hamiltonians. There I developed means to construct these metric operators, and even for the simple delta function, it fails sometimes. That led me to study these spectrosingularities and reconsider the whole scattering theory in 1 dimension. I showed you that the transfer matrix satisfies a Schrödinger type equation, and you can use it to construct optical potentials. This is optical potential engineering. I explained the relationship between adiabatic approximation and WKB approximation, showing that the geometric phases appear already in the WKB wave functions. And this can be used to develop higher order semi-classical scattering theory. I constructed, using these equations, an explicit model for unidirectional invisibility. I use them as building blocks to construct any potential I want with given scattering properties at a given wavelength. And this has various applications: reflectionless amplifiers, absorbers, phase shifters, threshold lasers, anti-lasers, and even invisibility cloaks. This is the last thing I did before coming to this conference. What do I mean by a cloak? So you have a scatterer, and you have an observer. You wanted this to be invisible. This can be done by putting another potential so that by interference it kills the effect. Obviously this is in one frequency, but this kind of devices will be useful in optical circuits because they work in one single frequency. Well, and this is the references, and this is for the invisibility clocks which I put on the web. Thank you very much.
There is literature of Russian school called inverse scattering. Are there any similarities between?
Not at all. No. You see, there the problem is not doing it for one frequency. So that's why I call it local inverse scattering. It happens at one, and it's much more difficult to do it. Even using those techniques to get this kind of effect is almost impossible, because what you need to do is to solve an integral equation. And you know, it's not easy. I mean, you can do it numerically, and that's precisely what has been done in the so many years that it was around. So this is completely in different directions, orthogonal directions to those. There are ideas that I have to put these together to get the full inverse scattering by using ensembles of unidirectional invisible potentials, putting them together to arrange to get any type of effect. But that's a project, and I have a PhD student working on it.
Maybe a physical question. There are various glasses which are transparent.
Yes.
On one side, and it's completely reflective, perhaps, on the other side. So do you say that they actually have the same
Transmission, yes.
transmission coefficient?
That's right. But this is linear optics. If you introduce nonlinearity, then the transmission is not reciprocal.
Okay.
So you can get non-reciprocity in transmission only using nonlinearity. Yeah. And that's actually very bad. I mean, this reciprocity is very bad. For example, people try to build optical diodes, but they can't because of this reciprocity. You have to invent nonlinearity or do something else.